Mysterious super-Earth discovered. Astronomers discover mysterious super-Earth planet emitting repeated signal from 154 light years away. Researchers has uncovered a fascinating new world, a mysterious super-Earth planet named TOI 1846b that sends out a repeated puzzling signal from 154 light years away. This newly found planet is nearly twice the size of Earth and weighs about 4 times as much. Let's get into the thick of it in today's AI podcast episode.
Okay, let's dive in. Imagine this. A signal, a persistent rhythm coming from 154 light years away.
A cosmic heartbeat almost.
Exactly. What you're picking up on is a distant world, a super Earth. Its name is TOI 1846b, and honestly, it's already making us rethink, well, quite a bit about how planets even form.
It really is.
So today, our mission, yours and mine, is to unpack this fascinating planet. What do its strange features tell us about the hunt for life out there?
And we've got some great stuff to draw on. We've been digging into the latest NASA findings, research from a whole global team, actually.
Yeah, we're aiming to give you the shortcut to understanding this really groundbreaking discovery. So, okay, this persistent signal, 154 light years out. What exactly are we looking at here? What was the first hint?
Well, what's fascinating, I think, isn't just the planet itself, but really the story of how scientists actually confirmed it exists. It really shows you just how powerful our observation tools have become.
Okay.
The first clue came from NASA's TESS satellite. That's the Transiting Exoplanet Survey satellite.
Right, TESS. It scans the sky looking for dips in starlight.
Precisely. And it detected this really consistent periodic dimming from the host star, like clockwork. Every March, they saw this little dip in brightness.
Just a tiny cosmic blink. So TESS, this amazing eye in the sky, catches that blink. But, I mean, how do you jump from that, from just the little flicker to saying, yep, that's definitely a planet? Seems like a huge leap.
It is a huge leap, and it takes a lot of work, a really rigorous process. It wasn't just TESS. Confirming it, officially validating TOI 1846b, involved a whole global effort.
Oh, okay.
The team was led by Abderrahmane Subkiu. He's at the Emitting Observatory in Morocco. And they didn't rely on just one thing. They combined methods.
Like what? What kind of methods?
Well, they used photometric data that's basically measuring the star's brightness really, really precisely to nail down the transit details. Then high-resolution imaging.
To make sure it wasn't something else interfering, like another star.
Exactly, to rule out background stars or anything else that might mimic that dimming signal. And crucially, spectroscopy.
Analyzing the light itself.
Right, analyzing the starlight spectrum. That helps understand the star, and it can also detect the tiny gravitational wobble the planet causes in its star as it orbits. It's that combination, that sort of cross-checking, that lets them say with confidence, okay, this is real. This is a planet.
That makes total sense. You need that confirmation from different angles.
Okay, so it's confirmed. Let's talk about TOI 1846b itself. We're calling it a super-Earth. What does that actually mean in terms of size and weight?
Yeah, super Earth is a bit of a catch-all, but this one is genuinely intriguing. It's almost twice the size of Earth, diameter-wise.
What's the size?
I mean, roughly 4 times Earth's mass. But here's where it gets really weird.
What?
Its size puts it smack dab in the middle of something called the radius gap.
The radius gap. I've heard that term. It's like a planetary desert, right? Yeah. We don't find many planets of that specific size. Exactly. It's this poorly understood size range. It falls between the small, rocky planets like our own Earth and the bigger, gas-rich ones like Neptune. And for some reason, planets in that intermediate size range seem rare.
So finding one in the gap, that's significant. It tells us something important.
Hugely significant. This raises a fundamental question. How does a planet even end up in this radius gap? What does that imply about, what it's made of, its atmosphere?
Right.
Planets like this are so important because they could hold critical clues about how planetary atmospheres form in the first place and how they evolve over billions of years. Why do some planets hold on to their atmospheres while others, maybe like Mars in our system, lose them?
Interesting, like a missing piece of the puzzle.
Sort of, yeah. It helps us test our models of planet formation. And adding to the intrigue is its orbit. It's incredibly close to its star.
How close are you talking?
It whips around its star in less than 4 Earth days.
Less than 4 days for a year. Wow, that's way closer than Mercury orbits our sun.
Much closer. So you'd immediately think, okay, this thing must be absolutely roasting.
Yeah, you'd expect scorching temperatures, right? Is it just a molten rock?
Well, here's another puzzle. Despite that super tight orbit, The estimated surface temperature is around 600 degrees Fahrenheit. That's about 315 Celsius.
Okay, 600 F is definitely hot, don't get me wrong, but maybe not as extreme as you'd guess for that orbit.
Exactly. It's hot, no doubt. But, and this is the kicker, scientists say it's not so extreme that it completely rules out the possibility of water existing there in some form.
Whoa, hold on. 600 degrees? And water isn't off the table. How is that even possible? This is where it gets really interesting for me. And you mentioned something about it being tidally locked. What's that about?
Yeah, it sounds completely counterintuitive, right? Yeah. It really shows you the sheer variety of conditions out there. The reason researchers think water might be possible comes down to a few things. Models suggest it could have a solid rocky core, maybe covered by a dense layer of high-pressure ice, and perhaps even a shallow ocean, or at least a thin atmosphere on top of that.
High-pressure ice, like not the ice we know.
Right. Exotic forms of ice that can exist at much higher temperatures under immense pressure. Now, the tidally locked part is key. Just like our moon always shows the same face to Earth.
Right.
TOI 1846b is thought to be tidally locked to its star, meaning one side is in constant daylight, facing the star, and the other side is in perpetual night.
Okay, so one side is permanently roasting, the other permanently frozen, or at least much colder.
Precisely. And that extreme temperature difference is where the water possibility gets interesting.
How so? It seems like the day side would just boil everything off instantly.
It would on the day side, but the thinking is that the night side would be significantly cooler. And depending on how heat might circulate perhaps through an atmosphere, if one exists, water could potentially collect or remain stable, maybe as liquid or ice, in those permanently shadowed cooler regions. Or perhaps in a transition zone, a terminator region between day and night.
Huh. So habitability, or at least the presence of water, might look very different on a world like this compared to Earth.
Absolutely. It forces us to stretch our definition of where water could persist.
Okay, that tidal locking and temperature difference makes the close orbit make a bit more sense, maybe? Let's talk about the star itself. What kind of star is TOI 1846b orbiting? Is it like our sun?
Not at all, actually. It's orbiting a red dwarf star.
Red dwarf. Okay, those are the small, cooler ones, right?
Exactly. Small, relatively cool, maybe about 40% the size and mass of our sun. They're much dimmer.
Which explains why the planet needs to be so close to get even that 600-degree temperature.
Precisely. For a planet to be warm enough to potentially have liquid water, what we call the habitable zone, around a red dwarf, it needs to huddle really close, much closer than Earth is to our sun.
Does orbiting a small, dim star like that make the planet easier for us to spot in the first place, using that transit method?
Yes, that's a huge advantage for detection. Imagine a planet passing in front of a star. The dip in brightness it causes is a fraction of the star's total light. Right.
If the star itself is smaller and dimmer, like a red dwarf, then a planet blocking even a small part of it causes a relatively larger percentage drop in brightness. It's a more noticeable blink for telescopes like TESS to pick up.
Ah, that makes perfect sense. A bigger shadow relative to the light source.
Exactly. And here's why studying red dwarf systems like this is so incredibly important for the bigger picture.
Why is that?
Red dwarfs are, well, they're basically everywhere. They're the most common type of star in our Milky Way galaxy. They make up something like 75% of all stars.
75%? Why?
Yeah. 3 out of every 4 stars are red dwarfs. So, if planets are common around them, and if some of those planets, even weird ones like TOI 1846b, could potentially hold water, well, that dramatically increases the number of potential places life might exist in the galaxy. Studying this one system gives us vital clues about countless others. That's incredible. So understanding this one planet has huge implications. Okay, we found it, we've characterized it. What's next? How do we learn more about this really intriguing world? There must be plans to look closer.
Oh, absolutely. The scientific community is definitely eager to follow up. The big one everyone's looking towards is the James Webb Space Telescope, JWST.
Of course. Webb's infrared eyes.
Exactly. Scientists are really hoping to point JWST at TOI 1846b soon. Its power lies in analyzing the atmosphere, assuming it has one we can detect. Webb could potentially spot the chemical fingerprints of things like water vapor, methane, carbon dioxide.
Key ingredients, or at least indicators for habitability.
Right. Those biosignatures, or at least atmospheric components, that could tell us much more about the planet's actual conditions of potential.
And what about telescopes on the ground? Are they still part of the picture?
Definitely. Ground-based observatories are still crucial. For instance, there's an instrument called MERO-X. It's at the Gemini Observatory in Hawaii.
What does MERO-X do?
It's designed for extreme precision, radial velocity measurements. Basically, it measures that tiny gravitational wobble the planet induces in its host star with incredible accuracy.
Ah, the wobble method again?
Yes, and those precise measurements do more than just confirm the planet's existence. They allow scientists to really nail down its mass. Knowing both the size from the transit and the mass from the wobble tells you the planet's density, which gives clues about its composition. Is it rocky, icy, gassy?
Okay, so density is key.
Very key. And there's another exciting possibility with these wobble measurements. They might reveal other planets in the same system.
Wait, really? More planets?
It's possible. In fact, the researchers mentioned that some of the early data, the preliminary radial velocity data, shows hints, just hints, mind you, of another gravitational pull in the system.
Another body tugging on the star.
Exactly. It could be another planet, perhaps one that's further out, maybe even in a cooler orbit that might be more traditionally considered habitable. It's still very early days on that, needs much more observation, but it's tantalizing.
Wow, another planet possibly hiding there. That adds a whole new layer. So studying this system isn't just about TOI 1846b then?
Not at all. And this discovery doesn't exist in isolation. It actually comes hot on the heels of another interesting find, TOI 715b.
TOI 715b, another super-Earth.
Yes, another super-Earth, this one about 137 light-years away, also orbiting a red dwarf star, potentially in its star's habitable zone.
Okay, so we're finding more of these worlds around red dwarfs.
We are, and studying planets like TOI 1846b and TOI 715b together helps astronomers tackle those bigger questions we talked about. Like, why do some planets manage to keep their atmospheres over billions of years while others get stripped bare? Understanding that process is fundamental to figuring out what makes a world truly habitable in the long run.
It's like building a library of these different types of worlds to compare them.
Exactly. And putting it all together, this discovery, combined with others, helps us piece together the grand story of how planets form, how they change over time, and what the conditions for life might actually look like across the galaxy, especially given, again, how incredibly common these red dwarf stars are. TOI 1846b might just be one example of, well, potentially billions of similar worlds scattered throughout the Milky Way.
Billions. It's mind-boggling. So let's recap quickly. We have TOI 1846b, a super-Earth, significantly larger and more massive than our planet, sitting in that strange, underpopulated radius gap.
Yeah.
It's orbiting a common red dwarf star in an incredibly tight, less than 4-day orbit.
Check. Very close.
Which leads to a hot surface, around 600 degrees Fahrenheit, but maybe not impossibly hot for water, especially because it's likely tidally locked.
Right. That day-night temperature difference could be key.
And future observations, especially with Webb, might tell us if it actually has an atmosphere and maybe even water vapor, plus hints of another planet lurking nearby.
That's the hope, yes.
Yeah.
It's a system that promises to teach us a lot.
It really pushes the boundaries, doesn't it? It makes you question our Earth-centric view. Which leads to a final thought, something for you listening to mull over.
Yeah.
Considering a world like TOI 1846b, tidally locked, extreme temperature side to side, yet potentially holding water, what does that make you think habitability really means? Could it look completely different from Earth? And if so, how does that change where and how we search for life in the cosmos?
Okay, what challenges do scientists face in detecting atmospheres on planets so far from Earth? Don't forget to comment it. Thanks.